In this lecture, we look at the superposition of waves. Superposition is when two waves add linearly. They do not change each other. That is, the sum of the two waves is simply a simple addition. So y1 is one wave, and that's added to y2. So, for example, we have these two blue waves, and they're propagating toward each other. We see that they're similar, but they're sort of reversed. As they pass through each other, you see the summed waveform, but after they pass through, they are unchanged. Let's look at the superposition of sinusoidal waves of different phase. That is, we have a y of xt, which is equal to an amplitude times the sine of kx minus omega t, plus another one with the same amplitude, but now with kx minus omega t plus a phase phi. So we have the red curve and a blue curve with a phase difference of pi over 4 shown here. The sum is the black curve. We see that they add together, producing a sinusoid. If we change the phase to pi over 2, it's still a sinusoid, though it's dropped a little bit in amplitude. If we go to a phase of 3 pi over 4, the black curve is still a sinusoid, but the amplitude is dropped even further. If the phase goes to pi, we have the sinusoid becomes a straight line. This is called fully destructive interference. In the case where phi is equal to 0 or 2 pi, then this phase leads to fully constructive interference. Let's look at this a little bit more carefully. We're going to look at propagating waves and standing waves. Is the sum of two sinusoidal waves propagating in the same direction also a sinusoidal wave propagating in the same direction? So writing down the form we had before, we have this y of x and t is equal to an amplitude times the sine of kx minus omega t plus an amplitude times the sine of kx minus omega t plus a phase. So both propagating to the right. We can use a trigonometric identity where you add two sines with different angles, alpha and beta, and that sum is equal to 2 times the cosine of 1/2 the difference between the angles times the sine of 1/2 of the sum of the two angles. Using that trig identity, for the first part we have 2a times the cosine of 1/2 the difference, and we can see that the kx and the omega t are going to cancel, leaving just 2a times the cosine of minus the phase over 2. Now we look at a second part of the trig identity, where the sine of 1/2 the sum. Here the kx's are going to add, and so are the omega t's, and the phase is left unchanged. So we have, this is sine of kx minus omega t plus 1/2 of phi over 2. So what we see is that these two co-propagating waves with different phases also has the same propagation. The result is a wave propagating in the same direction. What is different is the amplitude, and the amplitude depends on the phase, as we saw in our examples before. If, for example, the phase was pi, cosine of minus pi over 2 is 0, and that's fully destructive interference. What if the two waves were propagating in opposite directions? Then we have the case where you have a times the sine of kx minus omega t plus a times the sine of kx plus omega t, so we have one going to the left, plus a phase. Using the same trig identity, we have 2a cosine times 1/2 of kx minus omega t minus kx plus omega t plus a phase. The kx's still cancel, but the omega t's do not now. So we are left with cosine of minus omega t minus the phase over 2. And then looking at the sine term, we have 1/2 kx minus omega t plus kx plus omega t plus the phase. So in this case, the omega t's cancel, but the kx's do not. So we have sine of kx plus the phase over 2. So if we look at what happens here, we have the blue curve is propagating to the right, the red curve is propagating to the left, and the black curve is the sum. If we put a dotted line in there just to serve as a reference, we see that the black curve isn't really moving. It's just going up and down. So the sum is not propagating. It just goes up and down. So this is what we mean by a standing wave. So the two counter-propagating waves have produced a standing wave. And that's the end of this lecture.